Hello and welcome. This is Leetcode 167, two sum 2, which is a continuation of the infamous two sum problem, which is Leetcode number 1. The objective here remains the same from really taking a look at this problem where we are giving an integer of array. It's called numbers, and it's already sorted. And I don't know why they do this non-descending order wording. It's just a bunch of fluff, but don't let that confuse you. Sorry, my pin changed. And then basically it's the same thing. It's asking you to find two numbers in the list that add up to a specific target. The target is a given input into your function, where the numbers need to be in the list, and they cannot be the same. Obviously, they cannot be duplicates, and it's needs to be done. The trick here needs to be done in constant extra space. So what that means really is, instead of using memory to come up with a solution, we need to use a constant memory. So no data structures, just raw solution. And in numeric values, that means O of 1 space. That being said, let's take a quick refresh on the example here. So we got a list of numbers 2, 7, 11, 15, and you have a target, and the target is 9. And taking a quick look at this, you can see that, 2 plus 7 is equal to 9. So you will return the indices. And as you can see here, it's returning 1 and 2. And the reason why it's saying that, and I failed to mention this earlier, but it says that when you return the answers of the two numbers, you need to be added by 1. So it would be like I plus 1 and j plus 1 will be your result solution. Now, that being said, the brute force to this problem, in my opinion, would be just like if you were to solve two sum originally, you're going to use a double nested for loop. So you would have one for loop that would iterate through the array numbers of 2, 7, and 11, but it'll start at 2. So you have 2, 7, 11, and 15. And the target is equal to 9. So you'll have I starting here as a first for loop, and then another for loop, which is a nested for loop that will start right at I plus 1, which is j, which would be right here. Now, luckily, since the numbers are fairly in the solution are very close, it would return us right away. We would get 2 and 7. But for sake of argument, we're going to explore another example here really quickly that talks about how this algorithm will look when things tend to be far apart. It will look pretty aggressively and very time consuming. So let's do a 2 plus 3, or sorry, not plus, but 3, 4, we'll do 6, and we'll do 10 and 15. And the target here, we're going to do 10, actually. Oh, there we go. So as we said, I will start here, and then I plus 1, which is where the next for loop will start, j. And really, we're going to explore every single option until that j reaches the end, and it reaches right here. And we're going to start over, and I will be here, and do the same thing over and over until we find the good pair. But for argument's sakes, we're going to just run through this really quickly. So we got 2 plus 3 does not equal 10. 2 plus 4 is 6. 2 plus 6 is 8, and that is still less than 10. And then 2 plus 10, 12. 15 plus 2 is 17. So right now, our j and I will increment, and it will be right here. And as you can see here, this is going to keep on happening across all of the array until we hit a point where I is now 4, the value 4, not index 4, and j is equal to 6, and we will return this. Now, as you can see here, the only problem is your time complexity will be O of n squared, and it's a very extensive type of algorithm. It costs double the long time as compared to a different algorithm. But that being said, I will write up here really quickly how the solution looks like in the next window. So if we were to type this like in code real quick, it would look like, I'm just typing the core logic here. I am not typing the whole class and function definition. So it would look like, for I and for, as you have not noticed yet, I'm using Python here for these type of problems. So excuse me if I'm not using your preferred language. But yeah, going back to the logic. So we start the first loop, and then you got for j in range. And here we have I plus 1. Remember, because we're starting 1 ahead of the index I, length of numbers. And if we have here our check if numbers of I plus numbers of j equal to the target, then we would return I plus 1, j plus 1. And let's say we run into a situation where we couldn't find any option, although that hasn't been expressed in the problem, but to be proactive and just in case, we would return nothing really, return empty array. Now, that being said, what if there's a different approach that could be a lot better in time complexity? We don't have to do this whole double nested for loop. And there is. Now, this optimal approach, it's also optimal. Sorry, I'm going to write this out, is using the 2-pointer technique. And more specifically, it's the 2-pointer technique that is a converging 2-pointer technique, where you have 1 pointer starting at the beginning of the array and 1 at the end, and they keep on coming down the list until they cross each other. And once they cross each other, we have at that point completed the search in the array. All right, that being said, here let's take an example that we were presented with earlier. So we got 2, 3, we got 4, 6, excuse me, a little bit sick, 2, 4, 6, 9, and 12. And we're looking for a target value or summation of 10. So the way this algorithm will be, first you need to initialize and stating your pointers. So your pointers will be at the beginning of the array, which is right here. And then I'm going to put this right pointer right under this one. So I apologize if it's confusing, but you have a left pointer that starts at the far left of the array, and you have a right pointer that starts at the far right of the array. And what happens is we first check what is the current sum. So the current sum, which is simply numbers of value at the left pointer, and then we're going to get the value of the right pointer, and recheck. We check if current sum equals to the target. Then we would return L plus 1 and R plus 1. Else if we run into a situation where the current sum is greater than the target. So that means we have consumed a value that is the most extreme, the largest value on the right side of the map, right side of the array. And the reason why I'm saying this is because remember this, we are guaranteed to be giving an ascending array. So giving the right pointer is at the far end. So we're grabbing like the greatest value that we can. So if we get to this point where, our current sum is way bigger than the target, then we're going to say to the right pointer, hey, you need to decrement by 1. And what's going to happen here is, I don't need a reason right here. So we're going to shift this guy, and the right pointer will be here. And we're going to go through the same algorithm again. We're going to calculate the current sum. So 9 plus 2 is actually 10 here. So this algorithm will kick right now, right away. So we will get, no, sorry, no, wait, geez, no, that's, sorry, ignore me. Technically, it will be 11, not 10. So what happens is, again, we are greater than 10. So we're going to tell, hey, go to the right one more time, decrement by to the left. So we hit the situation where 6 plus 2 is 8, which is less than the target. So we're going to tell, that's our else condition, where we're going to tell the left pointer to increment by 1. And we're going to tell it to go here. So now we have the left pointer at 3. So 3 plus 6 is 9. So we got 6, 7, 8, 9, which is still less than the target. So again, we're going to tell it, hey, go move to the right one more time for me, please. So the left pointer will be 4. So 4 plus 6 is going to equal to the target, which will happen right here. And we're going to have one more addition to our logic here, where if we run into a situation where we have exhausted the search of the array, we would like to return none or return an empty array. But our solution should execute right here. This is where your solution is going to execute. So that being said, let's go ahead and jump right into the code in Leetcode and code this thing up and do a dry run there as well. Oh, and by the way, this solution is time complexity of O of n, because we don't have any nested for loops, and we're iterating through the loop once and kind of like in one linear way. And the space complexity is O of 1, because we're not storing any data. Technically, we are not using any type of data structure. We're just temporarily storing the value of the current sum. And we don't really technically need to do this. We can keep on copying this check num in our else conditions, else if condition, but just to make code a little bit cleaner, we're using a temporary variable to store such value. So again, with that being said, now we'll go jump right into the code and discuss it more. Hello, welcome back. So right here, we're going to try to code this solution up that we discussed right there on the board and the black or the whiteboard. And we're going to go over the technical definite solution to this problem. So without further ado, let's get right to it. So the left pointer and the right pointer initialization, if that's what you prefer to call it, is going to start at index 0, and then we're going to start at the far end of the list. So numbers -1, while left is less than right. That means as long as we want to keep iterating through the loop until we get to a point where the left pointer or the right pointer are crossing each other. And once they cross each other, we want to stop, because we don't want to reverse the order of the indexes or running into a situation where we're doing duplicates again. So that being said, we want to check what is our current sum at the moment, and that is calculated by adding the current sum value, or the value at the left pointer and the value of the right pointer. And if current sum is equal to the target, we would like to return that right away, but we need to add 1 into each of the pointer according to the solution. Else if current sum is greater than target, that's where we're running a situation where we have a variable that is a lot larger on the right side, and we want to start decrement that ordering from the right down to the left. And what we're going to do is tell the right pointer to start sliding down the way. Else, we run a situation where the current sum is less than the target, and we want to tell the left pointer to start moving upwards in the array, because again, this is a sorted array given provided by the solution, provided by the question already. So we don't have to worry about having like negative variables, or even if there was, they would be on the left side, not being on the right side. Hope that didn't confuse you. And then once we run into a situation where, oh, we ran through everything, but we couldn't find a solution, we want to handle the edge case by returning none. And that being said, let's go ahead and submit the solution. And as you can see here, it was accepted, it worked. And the time complexity should be, again, O of n, sorry. And as you can see here, that's the case. And the same thing with memory. It's going to be O of 1 because we are not storing, we're not doing a hash map or a hash set. We are using pure pointers and not storing any type of data structure into our set. So with that being said, I hope this video was helpful. And best of luck with your preparation and have a good one.